So in this question, we need to use the diagram from figure 16.39, and we have to find the net force between thymine and adenine in the first part and cytosine and guanine in the second part. Now, since the diagrams are really complicated, take, uh, I'll just write down the information which I need in this question. So from the diagram, we can see that the distance between O and N is 0.28. Distance between N and N is 0.3. So, and we are given in this question that the distance between any two atoms on each molecule is 0.1 nanometer. So we can find ROH to be RON minus 0.1, and we get 0.18 nanometer, and similarly RNH will be RNN minus 0.1, and we get it to be 0.2 nanometer. We do the same thing for cytosine and guanine as well, and we have the charge on the hydrogen atom and nitrogen atom to be 0.2 e, and charge on carbon and oxygen is 0.4 e. Now let's move to find the net force between thymine and adenine. So the net force, let's call this F net, will be a sum of the following forces which I'm gonna write. So that will be FOH minus FON, because this is going to be in the opposite direction of FOH, and similarly FNN plus FHN, and FOH is K times charge of O times charge of H, which is 0.2 E times 0.4 E over ROH square. FON will be K times 0.2 E times 0.4 E times RON square. And we do the same thing for FNN and FHN as well. So F net will be, I know that some of these charges are negative and some of them are positive, but we have already taken the sign into consideration by adding a plus or minus here. So OH has force of attraction, but ON has force of repulsion, opposite in the opposite direction. So we already took a minus sign here. Similarly, for NN there will be force of repulsion, and for HN there will be force of attraction in the same direction as FOH. So we have already taken the sign into account, and so we don't need to worry about the sign on the charges here. So F net will be then, let's take this, let's factor this out from this because this is a common value. So K times 0.2 E, 0.4 E over. Now all these distances are in nanometers, which we need to convert it into meters. So there will be a 1 into 10 to the power minus 9 square common in all of this distance. Now this will be 1 over, sorry, I did, let's find FNN and FHN as well because they have different charges. So FNN will be K times 0.2 E times 0.2 e over Rnn square. So this is not equal to this now. K times 0.2e times 0.2e. So now we can plug these values into this. So F net will be K e square over, say, 1 into 10 to the power minus 9 square, and in the bracket we have 1 over 0.18 square plus 1 over 0.28 square plus 1 over 0.3 square plus 1 over 0.6 square. Now we can solve this equation and we will get, let's move to the next page. So we get F net to be around 4.623 times 10 to the power minus 10 Newton, or 5 times 10 to the power minus 10 Newton. So this is the net force for between thymine and adenine. Now we will do the same thing for cytosine and guanine, and we'll write the net force here to be F OH. So there are two OH molecules here, so it will be 2 times FOH minus 2 times FON, because there are two molecules of two ON bonds here, minus F of NM plus F of HN. And here FOH is K times 0.4e times 0.2e over R OH square. FON will be K times 0.2e 0.4e over, sorry, this will be 4 and this will be 2 over RON square. FNN will be K times 0.2 2e times 0.2e times 0.4e over R and square, and FHN will be K times 0. Oh, sorry. So this will be 0.2 as well. So it will be 0.2e times 0.2e over R HN square. So we can take Ke square common from the whole thing. So we have Ke square over, this comes from converting the nanometers into meter in the distance. So it will be 2 over 0.19 square minus 2 over 0.29 square minus 1 over 0.3 square plus 1 over 0.2 square. And solving this, I get F net between guanine and cytosine to be 7.116 times 10 to the power minus 10 Newton, or nearly equal to 7 times 10 to the power minus 10 Newton. And this is the force between cytosine and guanine. Now, in the last part of the question, we have to find, so in the last part of the question, we have to find the total force for a DNA molecule that contains 10 to the power 5 pairs of such molecules, assuming that half of it is 80 pairs and half of it is CG pairs. And the total number of pairs is 10 to the power 5. So for the total, for this amount of pairs, 10 to the power 5, we have to assume they are equally divided between 80 pairs and CG pairs. So we average the above results and multiply it by 10 to the power 5 because this is the total number of pairs. So what I want to say is, so since half of the, so our total number of 80 pairs will be 10 to the power 5 over 2, and total number of CG pairs will also be 10 to the power 5 over 2. So the net force or the total force between all the pairs will be force of this amount of 80 pairs, or we can say net force of 80 that we calculated here times 10 to the power 5 over 2 plus force of Cg times 10 to the power 5 over 2. This gives 10 to the power 5 over 2 times F80 plus Fcg. And then simply we can plug these values into this equation and we get F total to be 5.85 times 10 to the power minus 5 Newton, or we can approximate it to 6 times 10 to the power minus 5 Newton. So this is our answer to the third and last part.